Okay, so for infinite geometric sequences and series, an infinite sequence is a sequence with an infinite number of terms. So in other words, it just keeps going forever and ever. Where an infinite series is the sum of the terms of an infinite sequence. In some cases, we will have an infinite sequence where as you look at the terms as they go on for a long time, they approach some number L. So if you see that the sequence seems to be closing in on a specific number, we say that that sequence converges. And whatever that number is, that number L converges to. If the sequence does not converge, it diverges. So later on in this semester, we're going to learn something called limits. And pretty much what a limit is what a sequence converges to, or sometimes when looking at functions, if as you close in on a specific number, or you look at as the function, the domain goes to infinity, does that function converge? And that is called a limit. So we'll be talking about that later in the semester, but that's pretty much what we're looking at right now. The limit as n goes to infinity, so as the number of terms approaches infinity of the sequence, if it is converging to some number, we say that it would be L. All right, so let's look at the first examples. What we're going to do is we're going to determine the common ratio for each one, and then we're going to state whether we think the sequence would converge or diverge. Remember, if you're not sure what the ratio is, all you have to do is take any term and divide it by its previous term to get the ratio. So in this case, we can see that the common ratio is 10. If you look at it, as we go across these terms, they seem to be getting further and further and further away from each other. We could see that the next term would be 2,500, then 25,000, and so on. So this is definitely not converging. It's getting bigger and bigger, so we would say this sequence diverges. All right, if we look at the next one, the common ratio is 0.5 or 1/2. So as we look across these terms, we go 100, 50, 25, 12.5, 6.25, and each term is half of the previous term. And we can see that these terms are getting closer and closer together. There's not as big of a difference in between them. And so if we continue to have these terms indefinitely, I think this would definitely converge. And if we continued this pattern, it would converge to 0. All right, looking at the next one, these are just alternating the same numbers. So the common ratio in this case is -1. We can't say it converges because it's not closing in on one specific number. So remember, if it doesn't converge, it diverges. Sometimes students get confused and they think it only diverges if it goes off to infinity or negative infinity, but that's not the case. It diverges if it does not converge. Looking at the next one, the R value is also negative because those terms are alternating signs, but in this case, we are multiplying by -3. So if we continue to do that, these terms, even though they keep alternating positive and negative, they would just get bigger and bigger and bigger. So we would say that this diverges. Remember, if you're not sure what the R value is, just take any term and divide it by its previous term to figure out R. So I want you to try the next 3 on your own. Pause the video, and when you're finished, start the video back. All right, so for the fifth one here, if we take the term and divide it by its previous term, we get that R is 1 over the square root of 5, or you can rationalize that to be the square root of 5 over 5. But regardless, as we continue to multiply by 1 over the square root of 5, or the square root of 5 over 5, these terms are getting smaller and smaller and smaller. And even though you've got these irrational numbers in here, you can kind of look at it right here, this number, we've got 25 here, this would just be 5 here, this would be 1 here. And so we can see these are getting closer and closer together. So we would say that this does converge to 0. The next one, the common ratio, is 0.01, or 1/100th is what it is. And it also is getting smaller and smaller and converging to 0. And the last one, the R value, is the square root of 2. So as we continue to multiply by the square root of 2 over and over again, these terms are going to get bigger and bigger, and they are diverging. So how can the common ratio of a geometric sequence be used to determine whether the terms of a sequence converges or diverges? If they converge, what value are the terms drawing near? All right, so pretty much, guys, anytime the absolute value of the common ratio is less than 1, in other words, the common ratio is a number between -1 and +1, the geometric sequence will converge, and it will converge to 0. Anytime you multiply by a number less than 1, it's just going to get smaller and smaller and ultimately converge to 0. If r equals 1, the geometric sequence will converge to whatever the first term was. Now, we don't see that happen very often, but just so you understand the second one, that would be like if I had the sequence 3, 3, 3, 3. Technically, we could say that the common ratio of that sequence is 1. So as I continue that sequence indefinitely, what does it converge to? It would converge to that actual term because it never goes anywhere. It would converge to 3. But recall, when r was equal to -1, like here in example 3 up there, we can see it diverges because it just keeps alternating. And anytime the absolute value of r is greater than 1, so in other words, it's a number bigger than 1 or a number smaller than -1, the geometric sequence will diverge. It'll either go off to infinity, or it will, even though it alternates signs, it jumps, but it's still going off to negative infinity and positive infinity as it jumps back and forth. Note, we're discussing the terms in the sequence as n goes to infinity, not the sum of the sequence. We're going to be talking about that in a little bit. So make sure you understand that these notes right here are about the terms of the actual sequence, not the summation of those terms, not the series. All right, so what I would like for you to do is I would like for you, for examples 1, 2, and 3 from up here, I want you to find the first 5 partial sums for just these 3. So remember, like the first one would just be 0.025. And then for the second one, you would add term 1 and term 2. For the third one, you would add term 1, term 2, term 3. After you do the first 5 partial sums for each of those first 3 sequences, I want you to decide, do you think that sequence would, if we actually did this series, do you think that it would appear to converge or diverge? Do you think the actual sums would converge or diverge to a specific number? So pause the video, try it, and then start it back. All right, so when I look at this first one, and this is our partial sums. So this is S sub 1, S sub 2, S sub 3, S sub 4, S sub 5. These numbers just keep getting larger and larger and larger. So I would say that this one, the partial sums would diverge. However, when we look at the second one, you'll notice that even though it's getting bigger, the sums aren't as far apart. So we are at 100, and then 150, and then 175, and then 187.5, and then 193.75. So even though it's growing, the terms seem to get closer and closer together. And so we would just make a conjecture here what we think it converges to. So I might say, I think it might converge to around 200. Of course, we'll try to figure out what exactly that would be later, but for right now, we're just making a conjecture. And then that third one, it just keeps flip-flopping back and forth between -4.2 and 0. So since it does not seem to be closing in on one specific number, we would say that that diverges. So looking at these 3, what would we say must be true for R, the common ratio of a geometric sequence, in order to have the sequence of partial sums converge? So in this case, the absolute value of R must be less than 1. Remember, what that's really saying, and that is saying that R must be a value between -1 and +1. But in this case, we wouldn't want to include 1, because if you go back to this sequence I had up here, 3, 3, 3, 3. If we started to do the partial sums, that would be 3, and 6, and 9, then 12, and it would just keep growing forever. So in order for the actual partial sums to converge, only this part can be true. Only the absolute value of R can be less than 1. And that's really, really important for these series that we're getting ready to get into. All right, so for some infinite series, the terms can be added to get a finite sum. Use the geometric summation formula for partial sums and let the absolute value of r be less than 1. As n increases and gets very large, what happens to each of the following expressions? So again, what happens as n gets really big, so as the terms go on forever and ever, if the absolute value of r is less than 1? Put an example up here where the first term is 1 and the common ratio is 1/2. You can see that as we keep halving on and on and on, these numbers get really small. So pretty much that's like saying if we say 1/2 to the 0 power, 1/2 to the first power, 1/2 to the second power, 1/2 to the third power, as n gets really big, what happens to each one of these values? Well, r to the n would ultimately converge to 0. Look at these terms here, how they converge to 0. So what would 1 minus r to the n converge to? Well, if r to the n converges to 0, then that would be 1 minus 0, which would ultimately be 1. So if we then substitute that into our summation formula for partial sums of a geometric sequence, that would be a sub 1 times 1 divided by 1 minus r, which would ultimately be just a sub 1 over 1 minus r. And that's where we get our infinite geometric series formula, but only works when the absolute value of r is less than 1. A real quick connection to AP Calculus. If a sequence diverges, the corresponding series will also diverge. However, if the sequence converges, the series may or may not converge. The only way the series is going to converge is if the absolute value of r is less than 1. So we're going to have to check for that each time. All right, so let's do some problems. For each infinite sequence that converged, find the sum of its corresponding infinite series. So from the front side, these were the sequences that actually converged. So I'm just going to go back through and write down the first term and the r value for each one. Okay, so anytime we are going to find the sum, the first thing we have to check for is that value of r between -1 and +1. So for this first one, we are good to go. And so then we can pop right into our formula. S equals the first term divided by 1 minus r, which is 1/2. So that's 100 divided by 1/2. So we would multiply by the reciprocal, and that is 100 times 2, which would give us 200, which is actually what we thought it might converge to, what it looked like it was converging to. So we've now proven that. For the next one, 1 over the square root of 5 is also a number that is between -1 and 1, so we can find this sum. So we would say 25 over 1 minus 1 over the square root of 5. And if you pop that in your calculator real quick, you could get that that is approximately 45.225. Remember, always round to 3 decimal places. And then for the third one, that is also between -1 and +1, so that's good. We can calculate this sum. So that would be 32,000 divided by 1 minus 0.01, and so that ultimately gives us 32,323.232, and that would be the sum of its infinite series. All right, so let's look at these next two. Remember, anytime you are doing sigma notation, always make sure you calculate the first term. Do not assume the first term like is 10, because it might not be, or 2 in the second one. How we know in this case that we're doing an infinite geometric series and not just a partial sum is because at the top it says to infinity. Be careful. Don't immediately pop into your new formula. You always got to check and make sure that r is a number between -1 and +1. All right, so why don't y'all try them? Pause the video, and then when you're done, start the video. Starting with this first one, we calculate the first term by substituting what it tells us in the bottom, which is k equals 1n, and we get that it's 8, and then we get that the common ratio is 0.8. Since that is a number between -1 and +1, we can find the sum, so we use our new formula, which is the first term divided by 1 minus the common ratio, which is 0.8. So that's 8 divided by 0.2. And so if we work that out, that gives us 40. Something you can also do is if you're using your calculator, you can type in the general formula for finding the terms. So I could just type in here in the y1, 10 times 0.8 raised to the x, and then I could go to my table, and I would want to look, starting at the first term, since that's where it wants us to start at, and you can see that the first term is 8. But be careful, sometimes it might say, well, start where k is 4, or start where k is 0, so make sure you're getting that first term correct. All right, so looking at the next one, if we calculated the first term, we would want to substitute 1 in, but before we do that, let's just check the r value to see if we can even do this. In this case, the r value is 4/3, and 4/3 is a number greater than 1. So the absolute value of r in this case is greater than 1. So if that happens, that means, guys, we can't do this. This particular series does not have a finite sum. If you were to write out all the terms of this sequence and then try to add them together, it's going to go off to infinity because it doesn't have a finite sum. Anytime the absolute value of r is not less than 1, we're not going to have a finite sum. So in this case, we would say the answer is does not exist. And you can shorten that and just put D and E. Just know that anytime you see that, D and E means does not exist. And that's why we always have to check on these, it has that little clause in it, that the absolute value of r is less than 1. So this next one is really funky looking because it's not in that general formula that we're used to seeing like the two above. So what we have to do is we're going to have to use some algebra rules, we're going to have to use some of our exponent rules to rewrite it so that it is in the form of a number times our common ratio raised to a power. So I'm just going to come over here to the side and kind of do this problem, the algebra, and then come back to it. So we have 4 raised to the 2n minus 1. What we're going to do is we're going to break that up. We're going to use backwards of our exponent rules. We know that when we multiply like bases, we add the exponent. So I'm going to go back and break this back up into the like bases that it originally was. So that's really like saying 4 to the 2n times 4 to the negative 1. But I'm just going to switch the order around real quick so I can get the n's in the back part. And then the same thing in the denominator. That's really saying 3 to the first times 3 to the 3n. I want y'all to think backwards real quick. If I'm multiplying like bases, I add those exponents. So if I went from this second step back to this first step, I would have said that's 1 plus 3n, which is what it is, 3n plus 1. Okay, so then, using my exponent rules, these numbers right here in front, this 4 to the negative 1 and 3 to the first, they're just numbers. They don't have any n's in there. So we know anytime we raise something to a negative exponent, we shift its position. So I'm going to change this part to be 1 over 3 to the first times 4 to the first. I can send that 4 down to the denominator. Then for the second part, I'm going to factor out that n part. So that's going to be 4 squared over 3 cubed, all raised to the n. So if we clean that up, that's going to give us 1 over 12 times 16 over 27 raised to the nth power. And then we can come back and rewrite our sigma notation so that we have it in this form. So we have n equals 1 all the way to infinity of 1 over 12 times 16 over 27 raised to the n. Again, we always want to make sure we go through and calculate that first term. So I'm going to come over here and do that real quick. If I want to find out what is the first term, because it starts out with n being 1, we would say that's 1/12 times 16 over 27 raised to the first power. And so ultimately, 1 over 12 times 16 over 27, 4 goes into 12 3 times, 4 goes into 16 4 times, and then if we multiply what we have left back together, that would give us 1 times 4 is 4, and 3 times 27 is 81. So again, be careful about that. The first term in this case isn't 1/12. The first term is 4 over 81. And then we can see r is always what's being raised to that power, so r is 16 over 27. r is a number less than 1, so we can pop into our formula. So that's going to be the first term, which we just calculated to be 4 over 81, all over 1 minus 16 over 27. When you get to calculus, you're going to have to be able to do problems like this without your calculator, so it might be a good idea to push yourself to not use your calculator. So that's 4 over 81, and then we would just pretend this is 27 over 27 minus 16 over 27, so that's 11 over 27. And then we would multiply by the reciprocal, so 4 over 81 times 27 over 11, and 27 goes into itself one time, it goes into 81 3 times, and so when we put this together, 4 times 1 is 4, and 3 times 11 is 33. And that would be the finite sum of this infinite geometric series. Okay, so I love this part of infinite geometric series. You can take any repeating decimal and figure out what its fractional value is by using these formulas. So for example, if we have 0.363636 repeating, it can be written as an infinite geometric series as follows. I personally like to break it up like this. 0.363636 is equal to 0.36 plus 0.0036 plus 0.000036, and so on. And then I like to rewrite it as a fraction. I'm more of a fraction person than a decimal person. You can do it either way. So this first one, 0.36, is really just 36 out of 100. And then 0.0036 is 36 out of 10,000. And then 0.000036 would be 36 out of a million. And you can just count the decimal places to figure out how many zeros that is. And so on and so on. So what I know from this is I know that my first term is 36 out of 100. And I know my common ratio is 1 over 100. Because every 2 decimal places repeat. So if I use our formula, the first term, which is 36 over 100, divided by 1 minus r, which is 1 minus 1 over 100, that gives us 36 over 100 divided by 99 over 100. And since both the denominators are 100, they would reduce. And if you want to multiply by the reciprocal to see that, you can. So we have 36 over 99. And then I would just say, okay, well, what is the largest number that goes into both 36 and 99? And that's 9. So 9 goes into 36 4 times, and 9 goes into 99 11 times. And I promise you, if you went in your calculator right now and you typed in 4 divided by 11, it would give you 0.36 repeating. And that concludes today's lesson.